Hi guys, today we will start test of hypothesis concept. I will just first introduce you what is the test of hypothesis and the null hypothesis, the alternative hypothesis, the errors that we are doing. So basic definitions basically. Then we will start my old videos. So I will finish recording this and we will go back to the last year's videos and we will see theoretically how we can derive the hypothesis test. We start with the randomized test and then we will see the most powerful test. Okay. Okay, let me go. Okay, so test of, sorry. Okay, so tests of hypothesis. Okay, so this is one type of estimation actually after the point estimation and interval estimation. So basically in those we are trying to find the exact value of the parameter using the sample information. But because of the sampling variations, we have to consider that when we have a sample, we might have different point estimates for different samples. So because of that, we need to take care of the variability within the sample. So we consider the interval estimation. So using the point estimates, we add the samples and then subtract the sample variation. In the hypothesis testing, basically, we are stating something about the unknown parameter. So we are stating that the unknown parameter value equals to some value or another value, or it is greater than or less than or not equal to some value. So basically, we have a statement. But basically, just giving one statement is not enough. So we have to have two statements because when we say that the value of the parameter equals to 5, for example, then what else? So could it be the reverse could be not equal to or greater than 5 or less than 5, or just state that not 5 but 6. Okay, so we have to consider two hypotheses. Okay, so basically a hypothesis is a statement about a population parameter, unknown population parameter. So this can be actually considered a linear model or non-linear model, and you try to estimate the values of the unknown parameters in simple linear regression, let's say, or multiple linear regression, let's say, or logistic regression. So basically we have a hypothesis there. So our beta I value equals to 0. It should be in the model or not in the model, not equal to 0. Usually we are considering two-sided test in that case, but basically we are doing hypothesis testing in that case. So basically the aim or the goal of hypothesis testing or hypothesis testing is to make a decision, actually decide which of the two complementary statements is true. Complementary hypothesis is true. Okay, but this should be based on the sample information, based on a sample from exactly from this population. Okay, so this is the key that we are using always, based on the sample information. Okay, so then we need to define our sample space first. So basically we know the parameter space, but our parameter space for the unknown parameter can be different from the parameter space defined in the hypothesis. So we will see this concept also. Okay, so let's start with the sample space. So sample space will tell us in our sample where our decision will be. Okay, so space of sample values. So this is the general definition actually. So I'm using lowercase letters, observed values of the sample, set of all possible outcomes, values of our sample random variables. Okay, so we assume that our observed sample is in the sample space. Okay, so this is a fancy A actually, so it's not just a set notation. So this is n dimension. Okay, so then this is a sample space. We also have a parameter space. Usually we use omega to represent parameter space. You know, this is a set of all possible values that the unknown parameter can take. All possible values of unknown parameter theta. Okay, so theta is in the parameter space. So we can have just one single unknown parameter or multiple parameters. Okay, so basically we have two hypotheses that I told you. So you already solved these concepts in your first grade, but let's summarize the results and then see the theoretical part, how to derive a test. Okay, so basically we have two hypotheses. One hypothesis is the null hypothesis. So basically it gives us the positive relation, or nothing changes from the regular behavior of the variable that we have. So current situation exists, okay, or everything is in the steady state. For example, when we are considering someone is guilty or not, basically we assume that everyone is innocent. Okay, so everything is in current situation, nothing changes. So null change, you can say. So we have null hypothesis. Okay, so we also have an alternative hypothesis. So we are stating that actually something changes. Okay, so we have an effect or the guy is guilty, or how to say, there's a difference from the previous situation. Okay, so I use H1 notation. Sometimes we are using HA, but actually the meaning is the same. So alternative hypothesis. Okay, so basically we have two mutually exclusive areas when we consider our parameter space. Okay, so our parameter space states that consists of actually the parameter space of the null hypothesis and the parameter space of the alternative hypothesis. Basically, we are partitioning our whole parameter space. Okay. So similarly, we can partition our sample space. So the one that we reject our null hypothesis, the critical region, or the not critical, so acceptance region, basically. Okay, so here, so we assume that for both cases, So these are mutually exclusive regions, and they give whole parameter space. And basically, again, we assume that there's no intersection between these. And similarly, we have the same situation in the sample space part. Okay, so this gives us the whole sample space, and the intersection of these will be empty set. Okay, so let's say this is our sample space. Okay, we want to separate it. Okay, so this is our critical region, this is our acceptance region. So in this case, in the sample, we reject our null hypothesis, and in this case, we cannot reject our null hypothesis part. Okay, so basically, we have two mutually exclusive sets. Or disjoint sets, so basically they are the same, you know. Okay, so in the null hypothesis, we are stating that our unknown parameter is in the null space. Okay, and this gives us the null hypothesis. And in the alternative hypothesis, we are stating that our unknown parameter is in the null alternative space. Okay, so this is like the case. We know that, let's say, the average production time of some product line is like 70 minutes. Okay, so we know that this is the usual situation, present situation. So nothing changes, null change. Okay, but in the alternative, we are stating that, okay, something goes wrong and the this product line runs more than 70 minutes. So this is our new situation. Okay, so we want to see which one is correct. Our, you know, when we look at the whole process, we might seem that it is greater than 70, but actually it might be 70. So so we need to take a sample, get the sample information, and based on this, we have to say which one is correct. Okay, the null or the alternate. So based on this, we need to decide. After deciding the hypothesis, based on this, we need to decide our critical region. Okay, so we need to define to reject the null hypothesis. Okay, so critical region, which is defined C, is a subset of the sample space which leads to rejection of the null hypothesis. Okay, so so based on our sample, basically we need to decide this. But usually in statistics, we want to say that actually most of the time, everything is in, you know, current situation, nothing changes. So we want to see, in many statisticians actually assume that this is the regular case and this is the most important thing that we should have. So it is better to fail to detect an effect or change when it exists than it is to conclude an effect exists when it doesn't actually. So because of that, mainly our testing procedures are based on rejecting the null hypothesis case. So we will talk about the errors later. So based on this critical region, we need to define, we have to do an action, give our rejection rule if our sampled variables is in the critical region, or not reject A0 if our sample is in the acceptance region. Okay, so this could be basically define our C. Let's say we have sample variables x1 to xn. Let's say 1 over n summation xi greater than some value a. Okay, so this will give us the condition basically to reject our null hypothesis. So we need to define the value a. So for some constant, so we can take a sample and calculate the value of the sample mean, and if this value is greater than a, whatever a is, then we can reject our null hypothesis or not reject. So basically our test defines the critical reason. Defines the critical region. Okay. So what is test actually? Also, so it is a rule. Is a rule which, on the basis of the sample information of the sample values, leads to a decision. As to either accept or reject H0. Okay, so usually we don't prefer to say, accept the null hypothesis because, it's a very strict rule. So sample to sample, again, like in the point estimation case, we can have, we may have different conclusions basically. So even if we can get only one case is that we can reject the null hypothesis, then it can be, not satisfy this assumption. So what we are saying, instead of saying accept H0, cannot reject null hypothesis. Okay, so usually we prefer to say it like that. Again, because of the sample variation. And we have some errors actually that we will see later. So basically, when we consider statistical hypothesis, is an assertion about the distribution of one or more random variables. So it's an assertion about the distribution of one or more random variables, specifying the values of unknown parameters. Okay, so basically we want to have some idea about where are parameters again. So with these hypotheses, we try to actually find the values of these. Okay, so we have two different definitions actually of hypothesis, two different types of hypothesis. So in one type of hypothesis, basically we specify the whole distribution of a random variable completely. Okay, so if the okay, so if the hypothesis completely specifies the distribution, then it is called a simple hypothesis. Okay, otherwise, so based on the type of the hypothesis, we have different methods actually to derive a test called a composite hypothesis. Okay, so what we mean actually, let's say we have theta and we have two unknown parameters. Theta is a vector, so we have a distribution with these two unknown parameters. So if we are stating our hypothesis based on just theta 1 and not state anything about theta 2. So basically we are stating that our theta 1 is 3, but theta 2 is unknown. So we don't know its value. So this is a composite hypothesis. Okay, so similarly, let's say we state that, sorry, it should be 0. Oh no, it's 1. It was correct. Okay, 1. Say, let's say it's 5. Even though we are stating the exact value of the theta 1, we don't say anything about the second one. So it's again composite hypothesis. But let's say if theta 2 is known, say theta 2 equals to 1. Okay, so this means that, so basically when we state that theta 1 equals to 3, means that we have x, 3 and 1 in this case, because we know the value of theta 2. So it becomes a simple hypothesis. Okay, and the alternative again. So we are stating that our PDF with these parameters. So it's a simple hypothesis. Okay. Okay, so based on the hypothesis, basically we can decide on the rejection regions. So let's say we have a distribution with just one unknown case. Okay, and let's say we have a simple hypothesis, mu equals to 5, which is simple. But let's say alternative is composite. Okay, composite. So one-sided hypothesis. So we can actually state this, let's say as theta 1 equals 7, like a simple hypothesis. Okay, so this is also possible. Or we can say that our, we are saying mu, sorry, mu and mu. Here also, let's say our null hypothesis is mu greater than or equal to 5 versus mu less than 5. Basically, kind of all of them give similar sentences actually. So these are very similar, especially the first one and the last one. So basically the test result will not change in this case. So what we are saying, so we have mu here, okay? So we are stating that our mu value is 5, okay? Actually, I said this one and this one. Okay, I forgot the example. Okay, so in the alternative hypothesis, we are stating that, so we don't have this value, but our value is greater than 5. So this is the region that we have. So when we consider this, actually, our null hypothesis, the parameter space will consist of gamma 0 and omega 1, where omega 0 states that our mu value is 5, and alternative space states that it's greater than 5. So basically, a combination of this will give us mu greater than or equal to 5 in the whole parameter space. So this part will be important basically. So we can have also two-sided intervals, and two-sided intervals basically have a very nice relationship between the two-sided confidence intervals. Also, we might have a vectorial type of thing. So like in the case where we could derive a confidence region for two unknown parameters case. Okay, so let's say in that case is we want to state that our mu sigma values equals to 3 and 5. So this is the case when we have a simple hypothesis, and in the alternative, let's say our mu and sigma not equal to 3 and 5. So this is a composite one. Okay, so not specify any value. So this is a relation. This part is related with the simultaneous confidence regions, basically. Okay. Okay, so these are the some parts, some type of hypothesis that we can generate. Okay, so let's focus on the thing. So we have the truth, okay, but we don't know that true value of the unknown parameter. So basically we are stating that in the null hypothesis, our theta value is theta 0. Let's say in the alternative, we are stating that it is not, or it is theta 1. So, but when we take a sample, based on the sample information, we might not get the correct decision on the true value of the theta. Okay, so we have to consider this the state of nature. Okay, so in reality, we can have a true null hypothesis. The value of the parameter is true in the null hypothesis, stated in the null hypothesis, or false. Okay, so H1 can be true. In reality, it can be like that. But when we have a sample, and based on our sample information, we might get different results. So we can not reject H0, or we can reject our hypothesis. Okay, so we don't know which one is true. Actually, we will never know actually, because we don't know the exact value of the population parameter. If we know that, then we don't need actually hypothesis tested, right? So basically, when our null hypothesis is true, and we not reject our hypothesis, then basically we are doing something correct. So if we have a correct decision here. Okay, and then when H1 is not correct, but we cannot reject the hypothesis, basically we are doing an error. Okay, so we have a type 2 error. Okay, so this is also sometimes known as false negative. Okay, okay, so another situation can be actually our null hypothesis. It can be true, but we need to reject the null hypothesis based on our sample information. So this is known as type 1 error. So we are doing an error here. Okay, so this is also known as sometimes the false positive. And basically when H1 is true and we reject the null hypothesis, so this will be our correct decision. Okay, so this is our state of nature. And we have to consider the probability of each these events. And we need to consider the probability of obtaining type 1 error and type 2 error as minimize them. Okay, so the probability of this gives us the alpha level, which is known as the significance level. Okay, and so this part is another error, and the probability of type 2 error is known as beta. Okay, and so the correct decision under this case is 1 minus alpha. And the correct decision, the probability of this correct decision is 1 minus beta, or this is also known as the power of the test. Okay, so we have a general power definition here. So when we consider, okay, let's write everything actually. When we consider the probability, the conditional probability, when H0 is correct, true. Okay, if we are not reject H0, Okay, so this probability is 1 minus alpha. Probability that A0 is true, but we are rejecting A0. So we are doing type 1 error. So probability of type 1 error is namely given as alpha level. Okay, so this alpha is our significance level. Okay, so this is known as significance level. So basically this part gives us our willingness to risk rejecting the null hypothesis when it is actually true. Okay, another case is the case when H1 is true case. So if H1 is true, but if we not reject A0, basically again we are doing an error, which is named as type 2 error, and we name it as beta. Okay, and okay, so as you can see, these two are, sum of them to 1. As you can see, 1 minus alpha and alpha, and similarly, the 1 minus beta, or the power function, and beta are make a complete set. Okay, so reject A0 when H1 is true. So this is a correct decision, and it is 1 minus beta, or the power of the tests. Okay. So basically we can derive everything under pi theta. So this gives us, this is also named as pi actually, but the general definition of power function of the test defined for all theta values in the parameter space. Okay, so basically this is known as reject A0 under all theta. So basically the definition of significance level alpha is also here. So based on our sample information, so our x1 to xn in the critical region given the value of theta. Okay, so these are our sample random variables, x1 to xn. Okay, so first of all, we need to specify our test. So once test is specified, then all properties of a test can be obtained from this power function. Okay, so alpha level, beta level, 1 minus the beta level can be defined. So basically we can compare the performance of different tests based on their power function. So different tests on the same parameter basically compared, like that we're comparing the different confidence intervals that we generate using different methods, their power function. Okay, so the probability of type 1 error basically can be defined by the power function where our theta is in the null space. Okay. Okay, or we name it as this one. Okay, so in our test, we want to maximize the value of this alpha probability under the null space. Okay, so we get the alpha. So we work with this alpha. So this is the maximum probability of type 1 error that we can get. Okay. Also, it is known as the significance level that I told you before. Significance level. Or it is also known as the size of the tests. Or the size of the critical region. And okay, so similarly, we can define the power function under the null hypothesis, alternative hypothesis, sorry. So basically, this is the probability of rejecting H0 when H1 is true case. So the correct decision case. Okay, so it is the 1 minus beta theta term, or the power function. So we want smaller values. Smaller values are desired because, you know, it is the error, probability of error. But in this case, we want to have larger values are desired. Okay, so basically, when we get this, and under the, so we get this value, and we get 1 minus beta term. So this gives us the worst possible type 2 error probability. Error probability. Okay. So also this means that we want beta type 2 error probability to be as small as possible. Okay, so we want to have a smaller alpha values, we want to have a smaller beta values. Okay, so a good power function should take large values in the alternative hypothesis region. Okay, so this means that we need to minimize both errors, right? But this is not possible. Okay, so let's look at the region we have, state of nature. Okay, so let's say here the null hypothesis is true, here the alternative is true. So here we have the critical region reject A0 and alternative hypothesis. So the probabilities are, we have 1 minus alpha, alpha here, and beta, and 1 minus beta terms here. Okay, so if we want to minimize alpha, okay, so what we mean that then we need to get smaller region in this case. Okay, so try to minimize this one. So this means that the area that we have for the beta getting maximized. So when we minimize this, okay, so when we minimize this, this will be maximized. So we will never minimize both errors. Okay, so it is impossible. So then what can we do? The idea that we are using is, okay, just fix one of them. Okay, so fix one of them and minimize the other. Okay, so fix one of them means that actually control the error rate of 1. Okay, so basically we need to decide then which one should I have to fix, which one that I have to have its control. So I can control one of them, and then based on this controlled level of the probability of error, I need to minimize the other probability. So how can we do that? So we need to discuss then which error type is more important than the other one. So theoretically, we are always stating that type 1 error is much more important than the type 2 error. And based on that, we fix the alpha significance level and then derive your test to minimize your beta or maximize your power. But in reality, it's not like that. It's more complex. So we have to be very careful about the situations that we have, okay? But all the theory is based on this one. So basically, so which one to fix? Or control. Okay, so we need to decide this. And many statisticians state that it is better because in null hypothesis we are stating that the present situation holds, okay, so nothing changes. But in the alternative hypothesis we want to see an effect of something, okay, any change. But in many statisticians or the statistical theory based on this principle, so it is better to fail to detect the change or effect, okay? It is better to fail to detect an effect or a change on the present situation when it exists than it is to conclude an effect exists when it doesn't. Okay, so basically this says that the detecting an effect when it exists is the type 2 error actually. Okay, so this states type 2 error case. But conclude an effect exists when it doesn't, so reject H0 when it doesn't actually. The type 1 error, right? So in this case, usually whole theory is based on the case, the type 1 error is more important. Type 1 error is worse than type 2 error. Okay, so all theory is based on that. However, reality is much more complex. You need to be careful. About your decisions. Okay, so let's consider one example. So let's say we want to assess the strength of a new jet engine part. Okay, it is under consideration. So people's lives are raised on the parts of this strength, right? And false negative in this scenario, so the type 2 error basically merely means that the part is strong enough, but the test fails to detect it. Okay, so this situation does not put anyone's life at risk in this case. On the other hand, so this is type 2 error. So in this case, type 2 error not important, but type 1 errors are worse in this situation because they indicate the part is strong enough when it is not. Okay, so people's lives are at risk in this case. So in this case, type 1 error is important. So we need to control the level of type 1 error, false positive. But let's consider this example. Now, suppose that the jet engine part is already in use, okay? But there are some concerns about failing, okay? And in this case, you want the test to be more sensitive to detecting problems even at the risk of false positives. So in this case, type 2 errors are worse in this scenario because the test fails to recognize the problem and leaves that problematic part in use for longer. So this means that actually type 2 error is more important than type 1 error, okay? So using hypothesis tests effectively requires that you understand their error rates. And by setting the significance level and estimating your test power, you can manage both error rates so they meet your requirements. Okay, so basically this is nothing wrong with fixing the alpha level, but you have to be careful about what type of error is more important in your case. Okay, using the regular statistical theory, the belief in the statistical theory, we assume that type 1 error is worst case, but even though the other case is okay, we can set the significance level and estimate the power of the test. Okay, so based on that, okay, so fix alpha. Okay, so give a small rate like 5%. When the situation is more risky, give 1%, and then minimize or maximize the power. Okay, so this is the regular cases that we can do. Okay, so type 1 error is fixed actually, so we cannot do anything. But type 2 error, the reasons of type 2 error, so type 2 error depends on the sample size and basically the variability in the data. So if you have a small sample sizes and high variable data, then your type 2 error will be high in that case, okay? So to be able to get smaller for a fixed alpha, to be able to get smaller type 2 error rates, you may need to increase your sample size, okay? Or just apply a transformation on your sample to get low variable transformed data and do the test on these, but it will be on the transformed series actually. So you have to go back to the original levels at the end. Okay. Okay, so let me see. Okay. Okay, so increasing the sample, increasing the alpha level, increase the sample size, and checking the variability of the data, or getting the homogeneous ones, maybe applying stratification in your cases to reduce the variability might be important things. Okay. Okay, so for example, we want to test a hypothesis. Okay, and we want to get the power function. Okay, and we want our hypothesis. Null hypothesis states that our parameter value is in this region, and alternative states that. So this is the null hypothesis. This is the alternative hypothesis. Okay, so this is the value of the test. Okay, so let's say in this case is basically under the null alternative hypothesis, we want to see actually our power function getting its maximum levels or higher levels. Okay, so this still goes 1. It's probability no. And let's say we state that in our null hypothesis, our theta value is less than or equal to 4, and alternative is theta greater than 4. So let's say this is 0.4. So this level here gives us the alpha level. Okay, so this length is here alpha. And at this point, okay, this part shows us the power function at the values. So here, these parts are the beta values, okay? You know, this part gives us the power function. Theta in the alternative space case. Okay, so this is how we derive the test, but based on the direction of the test, we have a different situations. For example, so let's say we have this power function, but now the hypothesis is the reverse, let's say. So we want to see the null hypothesis, we have this, in the alternative we have this. So we want to have a higher regions here. So this is the value 1. And here, let's say again the 4. So let's say we want to test theta greater than or equal to 4 versus theta less than 4. So now this value gives us our alpha. And now the region here, this part, gives us the power function theta, where theta is in the alternative space, the higher values that we accept. Okay, so this is the alpha level that we have. And the region above the curve gives us the type 2 error probabilities. Okay. Okay, so let's skip these examples. Another concept actually is as the p-value. Okay, so let's talk about also the p-value. Okay, so I don't have that much space. I will erase the last thing that I wrote. Okay. Okay. Get rid of this and give some information related to p-value. Okay. Okay, so p-value is very important. Basically, nowadays we are using computers a lot, and hypothesis test results based on the results of the computers that we give us actually. So the importance of p-value increased. Although nowadays statisticians believe that the p-value should not be stated as the result of the hypothesis, the rejection mechanism of the hypothesis, decision on the hypothesis. Still, we are using them actually. So what is p-value? So basically, it is the value of rejecting the null hypothesis, reject a zero region based on the sample information, or we can say that it's observed significance level on the reject A0 based on the sample information given A0 is true. Okay, so it's like a definition of the type 1 error probability. But in the type 1 error probability, we are just saying that reject A0 when A0 is true case. But here we are the rejection region that we give here as based on the sample information. So it is the observed significance level. Okay, or we can say that it is the smallest alpha level at which A0 can be rejected. This part is important based on the sample information, based on the observed value of a test statistic. Okay, Okay, so it gives us how much evidence we have against H0. Measures how much evidence we have against H0. Okay. Okay, so for example, we can say that, okay, so let's say reject H0 rule as, let's say, X bar greater than theta 0 plus Z alpha over 2 sigma over squared of n, let's say. Okay, so this, based on this rejection rule, what will be our p-value, how we will derive it? So X bar greater than observed value, okay, given that theta 0 is true, so theta equal theta 0. Okay, so this is the way that we are calculating. So we found a critical region to reject the null hypothesis. So this gives us our alpha level. Then we calculate the probability of this. It gives us alpha. Okay, but when we put an observed value of our test statistic here under this condition, then it gives us the p-value. And our general rule, basically, reject H0 if alpha is greater than p-value. Okay, so this is why this is always the case actually, but in two-tailed test we need to multiply this value by 2. So we will see that actually in some examples. Since I don't have any space, so I want to draw the picture here. Okay, so let's say we have this shape, and this is our, let's say, critical region, that here we will reject H0. Let me use a different color. Okay, so this is our C. So this is our rejection region, reject H0 region. Okay. Okay, so if our statistic is in this region, observed value, we will reject null hypothesis. If it is on the other region, then we will not reject null hypothesis. So consider the case where our alpha value, so this probability is alpha, right? Then let's consider that our p-value, the observed x1 value, let's say we observe, let's say this is x bar 1, is in this region. Then the p-value will be here, okay? So this is the p-value. As you can see, it's in the rejection region. So if alpha level is greater than our p-value, then our actually the observed value of the test statistic will be in the rejection region. But let's say we observe, oops, go back. Let's say we observe our sample here. Okay, so as you can see here, our p-value, the whole region that we have here. Okay, so in this case, our p-value is greater than alpha. As you can see, we are in the acceptance region actually under this case. Okay, so visually you can understand where you are, in which region, and then based on that you can decide to reject or not reject H0. Okay, so I will give my notes actually to you because I don't have these notes and the randomized test notes. I will just, get a picture of them and then share with you. Okay, so this is the end, but I will continue with the randomized test. Okay, so let's go back, stop sharing, and okay, guys, so see you on Wednesday. I will add also my last year's videos. Okay, so they are kind of primitive, and since we don't have a license for the Zoom, I couldn't use that in the recording, so I used my tablet to record everything, and the size of the videos are too big, so I had to separate them into 4, 5, 6 parts, like 20-25 minutes parts. If they are more than 25 minutes, I need to separate them the two, some of them like 50 minutes because of this reason. Okay, so so we will discuss everything in the course also. So after that we will discuss how we derive the test. So you know how to do it under the normality assumption, okay, or when we have a large sample cases. So again, we are using always the central limit theorem, and we focus on the z-test, t-test, chi-square test. But what if we have data from other distributions, okay, that we cannot convert them to normal distribution? Okay, so how can we get it? So for example, we are using a uniform distribution. So it cannot be, it's a rectangular distribution, so it cannot be, you know, normal distributed. So how can we derive our tests? So we will see that we will start with randomized tests, and then we will see the most powerful test, uniformly most powerful test, likelihood ratio test, and then finish the testing part with the likelihood ratio test. Okay, so see you guys on Wednesday in the class time. Bye.